All right. My clock has ticked 8 a.m. here in California, so we will officially kick off. I'll thank everybody for showing up today. Good morning, good afternoon, depending on where you are, possibly even a good evening if anybody's joining from Asia. Uh, I'm excited to kick off this year's webinar series, North American centric webinar series. There are also a European and Asian webinar series for current OS, but I think for those of you that might have dialed into last year's webinar series, what we try to do is really focus on what's going on, relevance, code and standards, action, engagement around North America. We will at times bring you a glimpse of what's happening in the other parts of the world where it's relevant or noteworthy. Today, we have a little bit of European flavor. We have Lawrence McKay with us from DC Opportunities. And I just recently started engaging with Lawrence. Very delightful and insightful. And then, of course, we have Brian Deckard from Siemens with us today. So, Brian, if you had the pleasure of being on the call last year, Brian is a frequent collaborator of mine, and a lot of people think Siemens and Schneider and ABB and eating all the big global manufacturers out here. We do a lot of collaboration as well as competition when it comes to the regulatory environment. So I'm very happy to have Brian on as it's always a good time when we get together. So today we're going to be talking a little bit about what happened at the Open Compute Project EMEA Summit in Barcelona this year. And hopefully we'll also get a look forward as to some of the collaboration that occurs between Current OS and OCP in the coming months, and really focus on that path towards scale today. So before we get into the meat, and I can say this is a pretty meaty presentation. We're going to get a little technical with you guys today. Sometimes we keep it at a little higher level. Sometimes we get down into the weeds. Today, it's going to be a little bit meaty today. So before we get going, just a couple housekeeping points. If you have questions, put them in the chat. If it's a relevant question to the presenter, what they're talking about in the moment, I will put that question out in real time. If it's something that I know that is coming up maybe a little bit later in the content, I'll hold on that question. Or if it's something that won't be covered later in the slide, I'll hold it to the back portion of Q&A, and we'll get to everybody's questions. We generally get through everybody's questions, so no need for any level of anxiety that your question won't be asked. We'll get to it. We'll be recording this session. We'll publish that at a later time as soon as we figure out how to cut off the front half where we're all talking about the weekend. We'll get that pushed out. But we're trying a new platform today. It's our first time on Teams webinar where we've used other platforms last year. So hopefully things go smooth and we don't have too many hiccups because of the platform shift. And remember to follow us. We're on LinkedIn, we're on YouTube. Don't know how you found us today. We appreciate that you're here, but check out the other content we have out there. There's a lot of great videos talking about direct current fundamentals and even some advanced topics. So get into the introductions. I think I already covered that on the intro slide, but if you're joining late, we have Lawrence McKay from DC Opportunities, CEO and founder, and a leading DC voice. And we have Siemens Brian Deckard, who is no stranger to the webinar series or the direct current community. He leads our work stream on the topic for current OS and is just a very informed expert on the topic. So for those that maybe have been following along, this might be a little bit of a repeat, but for those of you that might be earlier on your journey here, at Current OS, we're a global organization, a foundation for the advocacy of direct current power systems, and we also publish a design reference guide that we open up to members. There's a public version of that you can get off of our website too, but we've been collaborating with the Open Compute Project for probably a little bit 7-8 months now on what data center facility direct current looks like, and then a newer collaboration effort. We've been collaborating with ODCA, or the Open Direct Current Alliance, and I think bringing all those entities to the table really adds a lot of value. If you're familiar with the webinar series, this is generally where I show the Current OS logo screen, showing all the companies that participate, but we got a little different flavor for you today. We attempted to go through and cut up all of the logos from ODCA and Current OS and put them all on one screen. So apologies for making you squint, but really just want to carry forward that there's a lot of people talking about how do we make this future reality, and we have over 190 different entities, including more than 40 research or educational institution, certification groups, trade groups, and of course, for profit. So without further ado, I'm going to hand this over to Brian, and we can get into the content that you guys all showed up for today. Brian?
Thanks so much, Daniel. Go ahead and advance the slide. All right. So as Daniel mentioned, we recently came off of some great discussions within OCP EMEA in Barcelona, and we presented there some information about a look forward into the future of 800 volts and even beyond, data centers reaching to plus minus 750 volts, or a total of 1500, as well as a look back to the foundations that have been laid for DC microgrids in 700 volts, and really a lot of convergence, as you can see here, and alignment between Current OS, Emerge, ODCA, in the existing IEC TR 63282, etc., around standardization of voltage bands, and really this particular nominal of 700 volts, which, as you can see in the blue circle on the left, represents a intersection with the 800 volts that is being considered in the data center space of this green area. This green area, as you can see, the common connection point or hardware anchor that we consider is 840 volts, where this is plus 5% of 800 as well as plus 20% of 700. Why does that matter? Because of the fact that standards such as the IT equipment standards already reference defaults of 20% for DC power. And so then the creepages and clearances that you would consider in your design for 700 volts can also accommodate 800 volts with a narrow high voltage tolerance. That being said, there are additional considerations as we look at the way that typically equipment is designed for, say, a plus minus 10% tolerance in AC. If you carry that over to DC, then you're extending beyond that green region into the yellow region. And with that extension, there are some additional considerations or challenges that you can see on the right. At the moment, IEC 62368-1 has a scope of 600 volts. It's and there is effort to clarify that scope as inclusive of a higher DC voltage. if you typically think about how, say, the low voltage limit works in AC, that's 1,000 volts, and in DC is 1,500. So that 1.5x factor typical. But here, actually, the scope clarification is for more or less closer to the peak square root of 2 factor, and that would put us at 850, which, as you can see, would be within and not actually reaching all the way to that 880 if you were to take a plus 10%. Additionally, there are a lot of designs and work so far that we could see on the floor at OCP EMEA related to sidecars, where there is a head start in the design. And so there's been a lot of consideration on the source of a sidecar that is nearby to a load of an IT rack. And that load of the IT rack then would be capable, say, to be able to have a wider range. But when we start considering the source, then we introduce additional challenges that have not necessarily been fully explored in terms of protective devices, as an example. So there's a need to look at the ecosystem as a whole. And with that, I'll go ahead and move to the next slide. So we have basically on the left a couple of different sources. Right now, as mentioned, this sidecar is the near-term introduction of DC into the data center. And as you can see, this has a shorter interconnect distance to a power shelf. And we're moving from power shelves, which are AC inputs, to power shelves, which are DC input. And why does that matter? Well, for one, you're taking out a conversion stage within the power shelf. And so ultimately, we're able to scale up the power of that power shelf. But beyond that, as you can see at the moment, right now, the AC power shelf is feeding 50 volts to the compute. And in a similar way, the DC power shelf will be feeding 50 volts to the compute. But long term, where is the bottleneck? Really, right now, we're talking about incredibly high currents as we scale data centers from not just triple digits kilowatts, but even into the megawatt territory. And with this, we have a need to consider the very practical, real thermal limitations of the 50-volt bus bar. And so this really helps to set the stage for a transition to higher, say, 800 volts power within the IT rack, and no longer necessarily that 50-volt stage. And as you can see, to complete then the picture and to reduce conversion stages and improve efficiency and so forth, there's the possibility to move beyond the sidecar into this tens and hundreds of meters of power distribution from a solid state transformer, or what's also starting to gain popularity as a TRU, a transformer rectifier unit.
Hey, Brian, first of all, I love how you extended the colors from your last slide onto this to kind of show that where those voltages are present. But when you talk about the medium voltage power supply or the TRU unit, does it matter what type of technology you're using to make that conversion?
So that's an excellent question. So really, there are a lot of possibilities that start to open up as we move into the SST or active space that enable things like our DC fault current to be reduced, that enable greater grid interactivity and grid support types of modes. One of the really interesting presentations at OCP EMEA was a presentation from EPRI with the DC Flex project, where one of the real challenges but real opportunities at the same time is the ability to consider that data centers do have a large need for power, but if there can be some flexibility in that power budget, and if there's the ability to move from designing for peak power to designing for a more flexible and demand responsive load, then we're able to increase the possibilities in terms of time horizons for when additional capability can be rolled out in terms of additional compute for the data centers. And so there definitely are some flexibility advantages and long-term, ideally, efficiency and so forth can be optimized in certain ways. But at the same time, this is relatively new technology, and there will certainly be advantages to being able to utilize what is well proven in terms of the more traditional transformer rectifier unit. So with
Awesome,
that,
thank you.
I was going to say also there, we won't maybe unpack all the details in this, but there are also some additional considerations that hopefully we'll be able to address in a further webinar on architecture impacts that you might need to consider with regard to grounding and so forth when you start paralleling the power sources and loads and so forth. So there's even more to come on that aspect.
Right.
All right, so moving to next steps. So we have really a couple of options that are on the table with regard to the load converters. And here you see that yellow icon trying to make the connection back to that previous diagram. So where microgrids have traditionally embraced the power limiting capability that you see with like this red line, where you can follow a power curve as voltage drops, and then as it drops further, reduce power. We recognize that this is not the only technology in use with data centers. And so for data centers, what we see is a lot of fixed ratio with point of load limiting converters, and these converters then are unable to continue to drop in voltage because it would have the effect of overheating. And so what is important to consider is that so far this range, which, apologies, that's a little hard to read, is say plus minus 5%. So that would put it at 760 at a minimum. And what becomes important there is to consider that long term, you would have a desire to be able to scale beyond 800 volts potentially in the future as loads continue to grow and the power within the IT rack continues to increase for the purpose of concentrating the parallel operations and achieving peak efficiency of data transfer among all those parallel processors, avoiding packet loss through conversion to fiber optics and so forth. So with that, there is there's more or less a couple of possibilities. One, you could take a D-rate hit across the entire curve to open up the voltage window, or another possibility would be to design in the first place for a little bit higher increase in the maximum current, so that you could in a forwards planning way be able to support full power at say a plus 750 with one converter and a minus 750 with another. One important point that I would highlight on this is that we've recently been able to enter a public input to the National Electric Code, whereby you can take a, say, 800 volts converter and add a restricted setting to this, such that you could put two of those together and still be within a low voltage installation context. So this is another important planning ahead type of measure that can help to ensure that we're designing for sustainability and reusability of equipment into the future. So moving from there, one of the interesting dynamics that is coming rapidly into the regulation scene is large load ride-through requirements. And as you can see, this is taking what has traditionally been in, say, double-digit milliseconds into triple-digit milliseconds and beyond for large load ride-throughs. Why does that matter? Data centers are typically having the ability to switch over to backup power to ensure that their compute is able to continue to perform the needed functions and not be interrupted. However, this switchover, if not coordinated properly, can result in the potential of grid stability events, as we saw relatively recently in the Northeast. And so there's been a high focus on what can be done to ensure that there is this better coordination between the loads and the grid. And so what's important then to consider is that if we're needing to ride through for longer durations, there could be benefits, say, into having a little bit wider voltage window for the operation of DC. And this then becomes important to coordinate the AC interface side, where you see here, for example, an interlink converter and its needed operating range versus what the grid is needing to keep on its side of the contract versus here as we move into the DC space. Now the DC outputs, power shelf, or in the future, say SST, transformer rectifier units, etc. Sorry, I said power shelf here, but I meant to say like sidecar, is needing to ensure that voltage is kept within a certain window for the loads like power shelves. And what we can see here is that this is not a problem that is new, but this is a problem that has been looked at before. And there were, say, wider voltage range considerations from perspective of, say, having batteries directly connected. So far within the scope of the OCP white paper on power distribution, we've been focusing on not actually having a direct connection of batteries, but through converters, which, as you can see, can sometimes then lead to a narrower range to consider. But in both cases, the interface is important between your source and your load. And so looking further to this, we can see that there is really actually, even though there are differences between traditional AC and DC, when you look to say distributed energy resources on the AC side, they actually have a wider range of voltage support to provide, then say a utility would be expected to keep the power within. And these wider ranges actually correspond fairly well to what is in the DC space. And so you can see that you can not only lay out the voltage with regard to a nominal and centering, but you also can consider it with regard to time. And a couple of important points as we look at this is that there is certainly a need for higher continuous voltage in a data center context, and really an optimization around that. And so with that, we consider that we try to keep hardware anchor points between the at least 840 volt point up here, where you can see the boxes are matching. And we also try to keep the lower anchor point, but preserve some flexibility. If you notice in here, there's derating possible for lower voltages, say, for example, less than 760 volts as a starting point. What is also important to consider is that, say, line losses have been previously handled as differently for the required voltage operation range for sources versus loads. That's preserved on the low side and now then introduced as well on the high side because we run so close to the maximum possible voltage. And then here, as you can see, there's a effort to look not just at 800 volts, but how this may scale into the future with 1500 volts, and where we may need to consider exactly what are the rules of how we abide within the low voltage limit. So moving forward from there, here is a look at the existing DC voltage bands that are within the current OS and within the ODCA system documents. As you can see, these do fit a wide range of operational voltage. And at the same time, they then, with that wider range, accommodates operation at 750, which was mentioned earlier as having importance in a plus minus 750 context. And at the same time, if we look at the 800 volt line, you notice that the operation ends here at 1 second and the operation ends here at 5 seconds. So operation continuously above 800, which is part of the data center Mount Diablo and PowerShelf specs, is something which would require adjustment from where things are today. It's not though that this can't be accommodated, because as you can see, this hits this 20% marker above 700 volts, and if we can keep that 840 volt anchor point, then this significantly simplifies the design considerations. So one other point I would mention here is that while this might look like a fairly large range, both from historical perspective of based on ETSI and what OCP has previously documented to support that, of up to 10 milliseconds. This is actually in current OS, we define certain zones based on how fast protection acts and how fault currents are handled and so forth. So actually, you have the possibility to shrink that needed continuous ride through to smaller levels when utilizing different forms of protection, as we highlight here in the possibility with solid state breakers in current OS zones 3 and 4, where those two zones are basically just differentiating whether you have multiple sources or a single source feeding. And so just continuing on that point, there is also then value to having the ability to widen up from say a plus minus 5% of 800 volt perspective to enable also the ability to hold up voltage if you have a wider window for it to be able to dynamically move within. So in addition to this, really comparing this proposal to what you saw before, the main differences are on the top end here, as well as this optional range, but highly encouraged range of additional voltage support. So the key point out of this, though, is that this is in alignment to OCP Mount Diablo with 820 volts for sources, as well as the OCP HPRV for PowerShelf presentations in terms of 840 volts continuous there. So there is this differentiation of source being a little bit less than load support in order to try to ensure that this maximum voltage is maintained. And with that, I'd like to hand over to Lawrence.
Thank you, Brian. Then let me see if I can take over control. Yes. Let's now continue after we heard from Brian about all the voltage consideration that we are very busy with. In the end, we can use these voltages in different ways in power system for DC distribution in data centers. And one of those things are different types of polarities that we can use. And then on the other hand, also the way how we earth our system also has an important impact. Here in this slide, we see the different ways on how we can have polarities in DC. We can, well, there's different wires that we use in, or different conductors that we use in DC. Typically, we have a symbol L plus for the positive line, L minus for the negative line, and then we can have an M or an N midpoint conductor that sits in the middle of those. Typically, the M or the N that's also used to be kind of close to ground, so it's kind of the one that is safe to touch under certain considerations and sometimes doesn't have to be protected. And then here we see on the right kind of, well, there's kind of different variations on how we can use these different conductors. On the right side, we see a bipolar system where we have a plus pole, a midpoint, and a minus pole. And that's kind of the most complete systems. And then we can have different variations of these systems. For example, we can distribute this middle conductor all the way. Then we have a bipolar system with distributed M. We can distribute it to some of the loads. For example, some loads are connected and have that. Some loads are connected directly between the plus and the minus. Then you can leave away the middle conductor. That's kind of the same thing as we do in AC, three-phase AC sometimes as well for big loads. Then we can also have a system where we don't have that midpoint conductor at all, where we don't only have the plus and the minus. And then we can have the unipolar system that have only one pole to ground. And of those, you can have the positive version and the negative version in theory. We see now often applied the positive version of those. Then for these different systems, here there's a couple of examples of how they can be grounded and I think or earthed. Here on the left-hand side, you see a bipolar system with a partially distributed midpoint conductor that is TNS grounded. In North America, that's called solidly grounded. And you see the grounding point there where the protective earth is connected with the M conductor. And in this case, it's supplied with two isolated converters from an AC grid, how it's drawn here. And then you see like the first two loads, they are kind of loads that are connecting to one of the pole. The first one is connecting to the plus and the M. The second one is to the L minus and the M. And then you have the third load, which is connected between the plus and the minus pole, but it also has the M conductor in the middle. And then the fourth load is just connecting between the plus and the minus pole. So you can, if you have a very big load, that makes sense, and you can save the M conductor. Then we have
Lawrence,
yes.
Can you provide us some examples? Like, why would you, like, I think in the AC world, most people are familiar when you might pull a neutral for a specific type, you know, a motor load or what, or, you know, if you wouldn't with a motor loader. What or why would you use the half voltage loads or the split voltage loads? Can you help provide some thought on that?
Yeah, I think that's a very good question. Actually, this is something that's very similar of what we do in AC as well. And there's different ways in AC that we do that. In North America, I think you have very often like this split phase system where you have the 120 volt and 240 volt, and that's actually pretty much the one-to-one equivalent of what we are doing here. So basically you can use the 240 between the one line and the other line to get more voltage, so you get higher power for the same current. And then you can basically use the one phase and the neutral to get half the voltage, and you can supply lower loads. And the reason why you would want to do that is basically that for smaller loads, there's a price that you have to pay for the higher voltage, and for smaller loads, that doesn't really compensate for the lower current that you get from the higher voltage. So that's why typically what you see is that for small loads, you connect them at a lower voltage, and then big loads, you connect them between the poles. In three-phase power systems that are more dominant in the IEC world, you have typically 230, 400 volts AC, right? Where then you have single-phase devices at 230 volts, and that's what is used for pretty much all the small stuff. And then big things you can connect on a three-phase load, and then you can, in some cases, you can leave away the neutral conductor as well, right? If you just have a factory with a lot of motor drives, then it's very common that you only distribute the phases, and that's kind of the same thing that we can do here. And coincidentally, this three-phase 400 volts AC gives you the same amount of power with the same current capacity in your conductors as the 700 volts AC, but you just save one conductor in the DC system.
Awesome, thank you.
Yes, and exactly, and then it's really about being able to connect devices of different power classes, different voltage levels in the same system without needing extra full power conversion for that. Yeah. Then we have on the right side as another example. So there's a lot of combinations of what he can do. This is just some examples here. We see like on the top we see unipolar system that is solidly grounded, where you then have only one voltage available. And then on the bottom right, you see IT grounded, IT earthed system with high impedance grounding to, so the system is in principle floating around. If there's a first fault, it could float such that there's no ground current. But in normal operation, it's kind of kept in the center. And now, after having looked at these different combinations that we can have, the question is now when we talk about data centers, so we have all these combinations of polarities, earthing, and voltages. And the question is, what is the impact of these system choices on the components that we have to buy or develop basically for these data centers? And then there's the question the other way around. If you're developing a new server or a new power supply or different kind of equipment for within data centers, be it pumps for the cooling systems or stuff like that, what kind of systems can you make your devices that you're developing compatible with? So what are the opportunities there on what kind of systems you can support with your R&D development? So we have been making this. So there's a lot of combinations there, and we have been making a very comprehensive table of different characteristics that we can be looking at. Here in this table, we start, this is just the headline of the table. So on the top row, you see the nominal voltages. You see here we use the 350/700 volts, 700, 700/1400, and 1400 volt that are the standardized DC voltages that are now internationally being standardized in globally in IEC. And then underneath we have 400, they are kind of equivalent to the 400, 800 volts, the 800 and 750/1500 volts that are now being used in the have been used in the data center discussions. Then we have the polarities. Do we have one pole that is different to Earth, or do we have two poles for bipolar? And then we differentiate if we have a midpoint conductor that we distribute or not. And then we have the earthing system, TNS for like the solid earthing, and IT for high impedance or floating grounding systems. And then basically we have all these different kind of systems that we have, in total 12 that we're comparing here. And then we put here some links for the to put that in perspective with the current discussion. So we have these first four systems that have been covered in the Mount Diablo spec. So that's then we have the 800 volts floating or TNS grounded systems that are covered in the NVIDIA architecture white paper. And then we have the 750/1500 volt midpoint grounded, TNS grounded system that has been presented by Google in OCP Summit in last October. And then maybe just to put it in some perspective, you have the bipolar TNS systems and the unipolar TNS systems that have been a lot covered in current OS. And then you have the one with the M conductor, and then you have the second system, which is the bipolar without M, that has been used in ODCA so far a lot. Including also the IT variant when islanding. And yes, so now let's see, what does this look like when we are, what is the impact of these choices on the materials, on losses and different components. So the first line that we see here is the wires that we use, and there is very evident, right? If you have a bipolar system with the M conductor, we have maybe more than two wires, otherwise we only have two wires. And why there's a 2-3 is basically because it depends. You either can distribute that midpoint wire only to some of the loads, like what we were discussing before, right? Maybe some loads they don't need it. And then otherwise, also if you can ensure that your loads are balanced, you can make it thinner than the other wires. So that's why there's a range there, where depending on how much you distribute it, you are somewhere between 2 and 3 wires throughout your whole system. In the next row, we look at the relative active wire material, and there obviously also the more wires we have, the more wire material we use, depending on the thickness that can vary. But then also as we go up in the voltage, you see on the right half of the table, we get a factor of 2 lower current, basically, because our effective voltage in our power system is higher. So we need to distribute less current, and in order to carry that with only half the current, we in principle only need half the copper. for that. So that makes a big difference there. Then if you look at relative losses, we have a similar picture that obviously also if the voltage goes higher, the losses go down. Here we assume like the same current density in the conductor. So that's why if the current, the voltage doubles here, the losses kind of half. Obviously, if you would use the same conductor material, so if you don't take the savings in the line above, then you would only get a quarter of the losses. But basically, in this case, we distribute the benefits of the higher voltage, half to the losses, half to the material savings. And then these relative losses, it's very important there in where we have the 1 to 2, that is only in partial load you get a different percentage in losses, right? But that is effectively you still have lower losses because this unbalanced load we assume here you will only get if you have not full load. So you'll design your system for full load balanced operation, and then if it's unbalanced operation you get a bit different relative losses. Good. Then we're talking, next row is the currents. Very simple. Voltage goes up, current is half. And then we have the number of protected poles. And there's basically in some systems you need to protect more poles. In the bipolar system you need to protect at least 2 poles. In unipolar systems, if you do TNS grounding, you can also get away with protecting only one pole. And then what is important next, if you're thinking about solid state breakers that are very interesting for data centers and DC in general, it's important to think about, okay, what kind of voltage do they need to block? And there are some systems, especially the unipolar systems and system with M conductor, they can only block 1 pole voltage, whereas the other breakers, they need to block the pole-to-pole voltage. So that's the difference there. And then semiconductor breakers are in principle a bit pricey, so it's kind of good to, and they also have impact on losses of the system. And there's a multiplicator there that's basically the current that you have to protect, the voltage that you have to protect, and how many of those breakers or switches do you need. And the multiplication of those is this figure of merit that we have on the bottom, and basically there, what you can see is as you go up in the voltage, yes, you need more voltage in your thing, but then also the current goes down. So there's different systems, but then the different earthing systems, they result in different voltage semiconductor area that you need in your breakers. In general, for all these tables, you can find them in the white paper. Lower numbers here are better. Then there's another aspect, and that is the density, and that's one of the main drivers for DC in data centers is the volumetric density to get more compute power in the rack. And here what we see is that as we go up in voltage, you need more space to make sure that everything is safe. And it's mainly the space towards your enclosure that is having a big impact here. And you see the first 2 systems, they have the lowest clearances because they have a very low voltage to ground, only 350 volts nominal. If you leave your system floating, you need to design for the worst case. And then obviously, if you go to a higher voltage, you need a higher clearance as well. Now, the interesting part is here that these 4 systems that are now highlighted, they have all the same requirements for clearance and creepages. And so what you can see here is that basically as soon as you consider floating IT grounded system or high impedance grounded systems, you need this extra clearance to have, let's say, the 700 or 800 volts to ground. But then if you go to the most right one of the highlighted columns, then you see that to get to the 1500 volts, which is the low voltage limit, we already can do that with the same clearances that we are considering for the unipolar 800 or the floating 800 volt systems. So, and I think here the main message is we can already design systems that make full use of the 1500 low voltage range with the stuff that is being considered and designed right now. And so there's not a next safety level or something else. It's already doable with the systems that we are looking at right now. By the way, the gray columns are the ones that we consider that are not likely to be used in data center. Yes.
Now, just this box that you're highlighting, the point you're making right now, this ties back to Brian's earlier Venn diagram slide, correct? This is sort of showing that same sort of sweet spot of interoperability.
Yes, but actually the real point that is pointing to is if you want to operate at the 1500 volts, you need to make sure that you're operating under the 750. And that's kind of what is highlighted here on this slide, where we can see what devices you can develop. And if you're now making 800 volt devices, you can obviously operate them in the first two systems. If you want to operate them in the other four systems, you need to design them such they have the extra clearance to Earth. But then the last one of these systems, you need to make sure that you can operate under 750 volts as well. And that's what Brian was highlighting, is to make sure that if you put two of those systems on top of each other, that you're still under the 1500 volts. And that's basically something you can design in right now. So you get ready for those systems. And in that way, you can make use of the full 1500 volts. Oh, sorry. So basically, you can get ready for that and design appliances right now that are ready with all these to operate with all these systems. The important message here is that devices that are now being designed for 800 volts that are also designed for IT grounding or unipolar TNS grounded systems, they automatically meet the requirements that you need for 700/1400 volt TNS grounded systems. So that allows you basically then to use the full 1500 volt range in your data center, which is kind of the limit of low voltage, which quite surely we don't want to go above with the servers. Then the second point is, in order to allow that, you need to make sure that you can operate underneath 750 volts as well, because you want to stay underneath that to stay under the 1500 volt range. And then what Brian was mentioning is, if you have a source, you want to have a setting to make sure that it stays under 750 so that you for sure stay within the low voltage range. And then the third point is this extra range that we're talking about. Probably we will be very happy about having that flexibility in future anyway, because as we extend the size of the DC grid, we can expect that there's a lot of more fluctuations and things happening in our DC grids, where we will be very happy if you have a little bit more margin to the top limit of what our converters can handle. And Daniel, with that, I hand it back over to you.
Yeah, and thank you so much for Lawrence. I think that last point really brings it home when for people that are designing systems out there or product out there to go into these systems, something we really want to keep in mind. So there are a few things coming up that I think or tie into what we're talking about. We have a IEC standardization effort. And a lot of what we're doing across North America and Europe, we're trying to keep uniform architecture, not recreate the problems we have in alternating current. So please scan the QR code if you'd like to join the session coming up on May 26th. And then if you want to join Current OS partner programs, we have some options. If you're want to clarify any of this, just head to our website, and there's some handy information there to guide you through how this might help you as a manufacturer decode and ensure your products are interoperable and compatible for future designs, as Lawrence was alluding to. And then if you want to join Current OS quick enough, you can catch our next coming internal General Assembly. We refer to them as plenaries, and it'll occur in Germany in May 27th and May 28th. And then beyond that, the next plenary, the 12th plenary, will be in North America, with details to be announced shortly. So now it's time for Q&A. Let's go to the chat and see what we have coming in. Okay, thank you, Rafael, for posting those links. That's great. If anybody has any further questions, though, feel free to type them out in the chat. Well, I think that that's a real good sign when you don't have a lot of questions. Will slides today be available? Yes, we'll be publishing the webinar here shortly. So thank you, Francis. And then Ricardo, are there standard testing descriptions for the holdup time like 62040? I'm not sure on that one. I'm going to phone a friend. Brian Lawrence, are you familiar with the testing?
So we did actually, I believe, if we go back to one of the previous slides, reference some of the 62040, I believe class 1 and class 3 power supplies. Maybe I'll
Here, let's see which one.
I believe that's in the AC slide that was showing.
No, I went too. Did I go too far? I think I went too far. This. Oh,
yeah. Now, yeah.
Here you go.
Oh, sorry. Yeah, you landed on it. So I think it's maybe a little bit hard to see, but up in that legend, we have the IEC 62040 class 1 and class 3, as well as we have additionally the standard ITIC curve and a couple of OCP specs that are additional reference points that really, I think, show the overall message that this is definitely a significant new ask coming into play. And I would also just highlight that this is a little bit variable in terms of different power utility requirements. This particular large load ride through was from ERCOT, but there's others, and
Good
they
point.
do vary. And so I know that there are efforts to kind of try to pull together some consensus on that as much as possible. But that is definitely a topic being further explored. There were those links within the toward the end of the presentation to participate in the Open Compute Project work streams. I'd also just put in another pitch highlighting that we've been advancing rapidly in the codes and standards, filling the gaps effort within UL in North America, and we're really wanting to kick things into the next gear on the IEC side as well. And so if you have interest in these types of topics like the IEC 62040 and other specific standards related to products and so forth, please do join in for that upcoming session. We look forward to having great participation from the audience and driving those topics that are important for creating a roadmap and pathway forward.
Yeah, excellent.
And Brian,
point,
maybe
Brian.
to add to that, I think right now also in current OS we have the converter group that's specifying the current OS testing standard, and I think the main question here is especially states because there we can get a lot of benefits in power quality, where basically you can get rid of a lot of these hold up requirements because we just ensure that the voltage doesn't go down much if faults happen in the grid. And I think so I think there we will also have some good initial requirements that maybe will be quicker than changing some other standards moving forward.
Yes, Lawrence, thank you. And I'm going to get through the time we have. I'm determined to get through the rest of these questions here. I think I got answers for those. So I do also want to say though that like last week we got a little more clarity around sidecar with UL, the announcement of 2878. So there's some clarity there. There's a question from Alexander: how far is the development of the SST or the spec Google announced? For SST, it's really MVPS, medium voltage power supplies, and we're on, I think, the 5th edition of that OI. It kind of set there for on the early end of that, but we're seeing acceleration through that standard, OOI. So I think that's coming along quite well. We also have a question here. What is the suitable safety standard for consideration of SST and SSCB? I mean, each of those has their own UL category from a product standard standpoint. And some of the safety standards work is tied to a joint effort that we're all participating with right now to advance the science around direct current arc flash. I would point you towards NFPA's Research Foundation for more information to follow up on the work being done for that. And we just kicked off, was that last Tuesday, the PAR within IEEE for the calculation methods for incorporating the output of the NFPA research into an IEEE effort around that. So, I mean, hot off the press, that's like a week old. Rajesh, you were asking testing labs available for providing out new products in this proving out new products in this category. Yeah, that one's a difficult one. There are various capabilities of the labs across the space. I think most of the testing facilities, or a lot of the testing facilities, are expanding their capability into direct current to be able to accomplish that. And that is a dynamic picture, so I can't really comment as to where anybody is with their releases, as there are quite a few labs. So I would just encourage you to reach out and ask for direct current capabilities. And the more people that ask at those independent testing labs, the more they'll look to invest in that bench. So we're at time. We're a minute over now. Gosh darn it. I thought I got through it, but the clock just ticks. And Ricardo, the final question, are there EMC standards already identified for the DC lines? We just created within the OCP work stream a new work stream focused on EMC within the last month. So that is a work stream that just got kicked off and is just sort of in the forming stage of that collaboration. So more to come on the future, and I think that you'll see some information on that. And then finally, Matthew, a question at 9:01. So that doesn't count against me. His question was asked at 9:01. Are there standards in place requiring isolation stage between the AC grid and DC distribution? I want to say technically no, but possibly yes on that one. Brian Lawrence, do you want to correct me on the interpretation of that question?
I would just mention that definitely as we consider like the transition to reaching to the extra low voltage, that's definitely a place where additional, say, reinforced insulation requirements come into play and are definitely worth considering. And we would definitely encourage looking further into the white paper and engaging further into that topic, because there's definitely more work to do as we move into 800 volts in the IT racks.
And then on the topic of AC to DC, there's different variants in there. There's different consideration. In principle, you can do it without isolation, but you need to think of more scenarios of issues that can go wrong. But I like to compare it a little bit with the PV sector, where initially you had a lot of galvanic isolation between AC and DC. And nowadays, most PV inverters don't have an isolation transformer anymore. So I think there's a little bit of similar development going on with AC and DC grids there as well.
Right. You got to keep your application in mind. No one's going to mandate it, but when you get into certain applications, it's a good idea. So we're at the end of the questions. 41 people still online. I'll keep answering questions until you people leave. But I think at this point in time, I'll wish you a good day and thank you for attending. And if you have any questions and follow up, you can send them to us, and we'll do our best to get to them. So thank you again for a wonderful webinar, and we'll see you next time.